In this session, we're actually going to go away from our lecture notes and focus strictly on linear regression. And today we're going to sit there and find out how to do a linear regression based on a set of data. Now, what exactly is a linear regression? You know, we talked about how not all models are perfect or exact models. Some will give us a great approximation. And that's exactly what happens if we sit there and plot our data points. We may look at our data and say, you know, this kind of looks like it forms a straight line, but it doesn't necessarily form a perfectly straight line. If that's the case, then what we want to find is the line that fits it best, or the line of best fit. And this is exactly what a linear regression does. Let's look at an example. Obesity is a risk factor for the development of medical problems, such as high blood pressure, high cholesterol, heart disease, and diabetes. How much a person can safely weigh depends on his or her height. This is actually a linear function. Body mass index, BMI, is a method of examining a person's weight in accordance with his or her height. Well, BMI is not a linear function. BMI is actually equal to the weight divided by the height squared. The relationship between height and weight should be a linear function if we hold BMI constant. So if we look at our set of data, say a BMI of 30 or greater can increase the risk of developing problems associated with obesity. Here's a chart that shows height and weight of people with a BMI of 30. Notice as the height goes up, the weight goes up as well, and if we were to actually perform the calculations for BMI, we would find out that each of these BMIs is approximately 30. What we want to do is three things. We want to find a linear function which shows how weight depends on height. We want to extrapolate the weight of a 78-inch tall person with a BMI of 30. When we say extrapolation, what we're doing is we have a data which runs between 31 and 73 inches. So extrapolating means that I want to find a point outside this data range, which 78 clearly falls above 73. And then we want to find the meaning of the slope of the line in part 1. This is how we're going to do it. Our first part, find a linear function which shows how weight depends on height. Since weight depends on height, then height is our x variable and weight is our y variable. And we're going to use the applet that I have here at this link. If we click on the link, we'll be brought to this website. This is a linear regression applet. And basically what we're going to do is just enter in our data. We said that height depends on weight, so we're going to go in our x variables and enter in our height. We simply type them in and hit enter after each one of these. And then we go over to our y variable and we do the same thing. Hit enter after each one of the y variables. Now, what we want to do is we want to plot these. We simply click on plot and it shows us this nice little arrangement of our data points. Now, when we go to do regressions, we're going to look at several regressions this semester. This one looks like a straight line, so we're going to assume that it's a linear regression. I will give you links to other regressions as well. The first thing we'll do is we'll enter in our data points and then plot them. You can also do this on your TI 83, 84, 84 plus calculator if you have one of these. If you don't, this link is provided for you. Now once we plug this in, we want to analyze it. Notice it gives us a line. This is what's called the line of best fit. Notice it does not touch all of these data points. In fact, it only touches, it looks like, 3 of the 7 data points. But this is the best fit for this line. We know equation for a line is y equals mx plus b. It gives us our m, 5.6856. It gives us our b, negative 188.8889. It gives us 2 other measurements, and we will talk briefly about the correlation coefficient. In this case, it's 0.9954. So, the first question that we had was find a linear function which shows how weight depends on height. Well, again, this gave us our m and our b, so f of x equals mx plus b. Our x was our height, our f of x was our weight. So this is our linear function. F of x equals 5.6856x minus 188.8889. The next part to the second question asked about the correlation coefficient. Your correlation coefficient basically tells you how well of a fit the linear regression is to the data. In other words, how exactly does it fit in there. Now, the correlation coefficient runs between 0 and 1, where 1 is a perfect fit. If you get a correlation coefficient of 0, that means there's absolutely no relationship between the two data. And anything in between basically tells us how strong the two variables are related. We look back down here, our correlation coefficient was 0.9954. which basically means this is a very strong correlation between height and weight. Next part was to extrapolate the weight of a 78-inch tall person with a BMI of 30. 78 is a measure of height. That's our x variable, so we simply take the function we were given, which was f of x is 5.6856x minus 188.8889. We plug in 78 for x, and we're going to get 254.5879. Please understand when you do these, you want to use the long decimal forms in each of these, and then when you get to the very end is where you will round. So when we interpret this, this means that a 78-inch tall person should weigh approximately 255 pounds to have a BMI of 30. The last part is what is the meaning of the slope of the line in part 1. This was our equation. F of x equals 0.56856x minus 188.8889. The coefficient of the x, the 5.6856, that's our slope. Remember, the x values was measured in height, which was in inches, and the y value was a measurement of weight in pounds. So if we look at our delta y over delta x, that's measured in pounds per inch. So this slope, the 5.6856, means that for every inch a person grows, they gain 5.6856 pounds to still maintain a body mass index of 30. Let's look at a second example. It says a ball is rolled down a hallway and its position is recorded at 5 different times. Use the data given in the table below to predict the location of the ball at t equals 10 seconds. We'll go back to our linear regression applet and we will simply plug in our data again. We know position depends on time, so time is our independent variable. So time is our x and the position is our y. Again, when we plot this, this looks close to a straight line, so we're going to assume a linear regression. We plug it in, and again, our correlation coefficient is 0.9986, which tells us it's a very strong relationship. So here's our slope, 2.378. Our y-intercept is 7.0122. So we plug this into our equation. It says use the data given in the table below to predict the location of the ball at 10 seconds. Well, 10 seconds is a time measurement. We plug in 10 for x, and when we get our final answer, we'll round, and we'll get approximately that f of 10 is 31. So it'll be 31 feet from the starting point at 10 seconds.